So quickly before we get into polymorphism, I want to, not fully, you're in lab, you're going to get fully introduced to this homework, but I want to just give a quick overview of the point of sale project. For point of sale, what you'll be building is a checkout system for a store, where a self-checkout system for a store, but without a scanner. We're not going to scan barcodes. Instead, the user has to input manually the code for each item. So if they want to buy something with code 123, they would click 123 and then scan, enter, which is going to simulate scanning an item with barcode 123. And then they'll be able to check out and get their receipt and see the total amount that all those items cost, including the tax, the subtotal tax, and total. So this is what we want to build. Nothing too crazy. There's some questions of how to do that and how to manage the data and everything, but not too crazy. This is something that, honestly could be a 115 project towards the end of the semester. You could certainly pull this off. You're adding numbers, you're computing tax. Nothing too wild there. What makes it a 116 project is that you can't use conditionals. No if, no else if, no else, no switch statements, no match case, no throw, try, catch, finally, because you can use those to simulate conditionals, and no well or do well, because you can use those, again, to simulate conditionals. And in general, any way that you're conditionally running code that you've written, if you write a line of code and then a line of code here, and you have some logic that says, if some Boolean expression, run this code, else run this code. If you have that anywhere in your code, that's in violation of the assignment, and there should be a 0 on the assignment. So you can't use conditionals. So this is a pretty strong restriction, and I want to say right off the bat, there's nothing wrong with conditionals. You should absolutely use conditionals outside of this project. There's nothing wrong with conditionals. But by banning conditionals, I'm effectively forcing you to use polymorphism, which we're introducing today. So I want you to use polymorphism, which is going to change the behavior of your program based on the types of objects, based on the type of an object stored in a variable, and not on a value of a variable. So instead of saying, if this variable has some value, run this code, otherwise this code, like a conditional does, we're going to see how to do that using polymorphism by saying, variable, do your thing, and based on the type stored in that variable, do one thing or another. So this implies that we can have a variable that stores different types, which we haven't seen before, which is polymorphism, which we're going to talk about today. So let's get to polymorphism. I don't want to add text. We now support file sharing. I was hitting the wrong button. Yeah, so polymorphism. So the lecture task today, we want to take the functionality from lecture tasks 2 and 3 and combine them into one feature in the item class. So in lecture task 2, you created a sale testing item and sales. The sale testing item was like the item class, but its sole purpose was just to test the sale class that you wrote. So you could test sale classes before we do this with the item class. In objective 3, you created 3 different types of modifiers that could be attached to an item, either a sale, a sales tax, or a bottle deposit, depending on what you wanted to add to that item. And those 3 things can modify the final price of an item or how it rings up in your register. Now we want to finally add that functionality to the item class. So now we want items to be able to have sales, sales tax, and bottle deposits added to them. And we're going to do that through the modifier class. So now that all 3 of those extend your modifier abstract class, we can modify the item class. We can change the item class to be able to have modifiers added to it. Whereas sale testing item, you could only add sales. In the item class, we're going to have that same functionality, but we'll be able to add any modifier to an item. So we want an add modifier, which is going to add that modifier, a price, similar to what we had in sale testing item, but this is going to give us the price with all modifiers applied, which I guess sale is the only one that matters in that case. And then tax, which is going to compute the entire tax of the item. So for each one of those methods, iterate over all the modifiers that have been added and call the price or tax methods accordingly and have all of them applied to that item. So that's what we want to do. Let's learn how to do that, learn what polymorphism is, how it relates to inheritance, how all this OOP stuff comes together to be able to give us some nice functionality. And I say this is like the last core concept in OOP. The next thing we'll talk about is the state pattern, which is an application of polymorphism and inheritance, which I use just to reinforce those topics. This is the last like brand new mind-bending conceptual thing that you're going to see in Learning Objective 2. So if you're feeling underwater, I think most of the class is a little bit underwater right now in terms of consuming all this content and understanding what's going on. Things move fast in this class. I know, I understand. I might as well address that a little bit right now. One thing about that is things won't get significantly harder. Like if you're struggling with Learning Objective 2, but you're surviving, you're going to survive the rest of the semester. If you can get through Learning Objective 2, I'm confident that you're going to pass the course. You're going to get through all of it. There's no big jump up in difficulty. Like from 115 to Learning Objective 1, I think there's a decent spike up in difficulty, mostly because you're getting a new language thrown at you really quick. From Learning Objective 1 to 2, there's a big jump up in difficulty. We just learned objects, classes, inheritance, polymorphism, references, heap, stack. That was part of LO1. But a lot of topics come rapid fire. A lot of really complicated topics, too, that come pretty quickly. We're not going to see that jump up again from Learning Objective 2 to 3 or to 4. Learning Objectives 2 and 3, in my opinion, are about roughly the same difficulty, but Learning Objective 3 is going to feel easier because you already survived Learning Objective 2. Once you make it through Learning Objective 2, you'll be stronger, you'll have more wrinkly brains, you'll be so much stronger going into Learning Objective 3 that it's going to feel easier. And then Learning Objective 4, I think, is a little easier than either Learning Objectives 2 or 3. So if you can survive Learning Objective 2, you're doing good. Don't get discouraged. This is the point where a lot of the class does get discouraged because so much content is hitting you so fast. Don't get discouraged. If you're surviving Learning Objective 2 at all, you're doing awesome. You're doing great. Even if like right now you're at the point where classes are starting to click and make a little bit of sense and references kind of make sense, I'd say you're doing okay. And then you can rewatch these videos and get caught up on all the material. That's fine. I didn't mean to go so long into this, but I think this is important. If you're still working on Pale Blue Dot, also don't be too discouraged. Just to share some stats, more than half the class is still working on Pale Blue Dot. More than half the class has not gotten the learning objective portion, the right portion of LO1 yet. So if you're not there, don't feel discouraged. You're not falling ridiculously behind. You're doing okay. You can make it. Persevere, hang in there, and you can still make it through this course. So, all right, enough of that. Unless anybody has questions, actually, let me get Chad up. You thought LO3 was the hardest because it's new info? I mean, LO3 might be the hardest if you've done OOP before. If you did OOP in high school and you did the AP, computer science, yeah, LO3 might be harder just because you've already done LO2. That doesn't mean it's objectively harder because you took an entire year in high school to learn 3 weeks of content in this course. So it doesn't, but if you've never seen OOP before, I'd say they're about the same difficulty. All right, so let's take a look at types and the type hierarchy. This is where we have inheritance, where each arrow means that class at the beginning of the arrow inherits the other. So byte, well, we don't really talk about byte. So int extends anyval or inherits anyval, and anyval inherits from any. So we can visualize the type hierarchies of Scala like this. And anything that extends anyval, those are values that are going directly on the stack, unless they're part of an object that's on the heap. And then everything else goes on the heap, anything that extends any ref. And those values, objects of those types, are stored on the heap. And then on the stack, we only store a reference to those objects. And this includes every class that we write. Every single class that you write, and anything that's not on this list, this is a comprehensive list of everything that goes directly on the stack. Anything that's not one of these is going on the heap and passed by reference. So we extended that type hierarchy a bit. We have physics object, which we didn't say extends anything, so by default it extends any ref. And then we had game object extend physics object, and then we had health potion and dodgeball both extend game object. So we expanded that type hierarchy, having physics object right here, extending any ref, and then our other classes below that, and then technically null extending each one of our classes, and then nothing extending everything. So our class went right there in the type hierarchy, and whenever we have an inheritance, we call this an is-a relationship, because whenever you inherit from another class, your type is that type that you extended. So if we look at the health potion class, health potion extended game object, so health potion is a game object. Game object extend physics vector or physics object, so game object is a physics object. Physics object implicitly extends any ref, so physics object is in any ref, and then any ref is in any. What we mean by that is that a health potion has 5 different types. It is 5 different types. And we can store an object of type health potion, or rather a reference to an object of type health potion, in a variable of any of those 5 types. So we can have a health potion stored in an object of type variable of type health potion, no surprise there. But we can also store a health potion in a variable of type game object, physics object, any ref, any. These two aren't very useful. You don't really want to do those in your code. Yes, technically you can. It's almost always a bad idea. But these ones we want to talk about. Game object and physics object. The fact that we can store health potions in variables, references to health potions in variables of type game object and physics object is going to give us a lot of power. And we get this power because of, and I'll show you examples of why this is powerful and why this is helpful. And we get this power because we used inheritance. We have these object types inheriting from other types. That allows us to use polymorphism. So inheritance, I do my best to motivate inheritance. You can factor out common functionality, yada, yada, It's not super compelling why you'd want to do that, and you probably might have left that lecture going, why would I use that? It's, he had decent arguments, but it's not that compelling. But this argument is compelling. The fact that we can use polymorphism is a huge reason to use inheritance, and this is where we get a lot of power out of our inheritance structures, out of our inheritance hierarchies, our type hierarchies. So this is polymorphism. Polymorphism, break it down, poly, many, morph, forms, many forms. So the fact that an object can take many forms, which means it can be stored in variables of many types, is polymorphism. Polymorphism is nothing more than this. So in your LO2 interview, a TA says, can you explain the concept of polymorphism, which I guarantee is a question they're all going to ask you. Explain inheritance and polymorphism are going to be questions you get. You'll say something like, polymorphism is when I have an object of one type stored in a variable of a different type. Bam! Nailed it. And then they're going to ask you follow-ups, like what does that actually mean, to make sure you really understand that. But that is polymorphism, that you can have an object of one type, which actually has many different types, and it can be stored in variables of any of those types. That is, in essence, polymorphism. Everything we talk about after this is going to be an application of that fact, but that is what polymorphism is. So there's one restriction to this. I'm telling you this is the greatest thing ever, but I'm going to lead off with a restriction. When you have an object stored in a variable of any type, you only have access to the state and behavior of the type of the variable, not the type of the object. So if I have a health potion stored in a variable of type game object, even though potion 2, that variable, is storing a reference to a health potion, I only have access to the state and behavior defined in the game object class and above, anything that a game object extends. So I have game object functionality, I have physics object, any ref, any. I have all that functionality, that state and behavior. But anything that I defined in the health potion class, I don't have access to from the game object class. Any state and behavior, especially anything that's named. Anything that's overridden, I have access to. But anything special to the health potion class, which in our case was volume, we can't access that. So that means this distance to player, which we defined in the game object class, I can say potion 1 of type health potion dot distance to player. This works, this is just fine, because health potion inherited that method from game object. So that variable of type health potion has access to that method. Potion 2 of type game object, well, game object directly has the definition for distance to player. So this is fine too. Game object has that functionality. We can call that method, everything's fine. But once we get to potion 3, this variable is of type physics object. It happens to be storing a health potion. So potion 3 does have a distance to player method. It's defined, it's there, it's sitting right there waiting to be called. But since potion 3, the variable, is of type physics object, we don't have access to this. In fact, this doesn't compile at all. We can't run this code. The Scala compiler will not let us. Can't run that code. So we don't have access to anything that's not defined in the type hierarchy of the variable, not the object. So even though potion 3, 4, and 5 have this method, can't access it because of the variable that is stored in. So the functionality goes by the variable type, not the object type. So we have one big restriction. So, okay, what's the good stuff? Why are we using polymorphism at all? So let's take a look at a few examples and see what we can do with this fact that we can have objects of one type stored in variables of another type. References to, of course. I often won't say the references to just because I don't feel like saying that many syllables, but it's always references to objects that are on the heap. So why use this? So let's take a look at our player class and make an observation here. We have this, oh, I missed one. That should say dodgeball. We have these two methods which are almost identical. They take either a dodgeball or a health potion, and they just defer functionality to that dodgeball or health potion with the exact same signature, the exact same call, the exact same code here. This is painful. Now every time we were talking how many objects we might want to add to this game, we might have hundreds of different object types that we want to add to this game. For every object type we add, are we going to add another method to this player class? Like, I don't want to do that. I don't know if you want to do that. But I sure as hell don't. I hope you don't either. You would have to add another method to this class, and then each time you add a new object, since you have to modify the player class, you should be writing tests, more unit tests, to test the player class, to test that method that you wrote, give it objects of that type, make sure everything's working, make sure you have all the functionality that you want, because you modified this class. We don't want to do any of that. So what we can do is replace those two method calls with just one method call, and instead of taking a health potion or a dodgeball, instead we're going to take a game object. Now, any game object that we add to our game has to extend game object. That's just the way we're going to organize our code. If it's a game object, it needs to extend game object, so it is a game object, and it can be an object that's added to the game. So useitem is going to take a game object. So we have a variable of type game object, and then when we want to call this method, and then of course the definition is the same. When we want to call this method, we can give it a dodgeball, we can give it a health potion, we can give it a bow and arrow, we can give it anything we want, as long as what we give it, whatever type object we give it, as long as it extends game object, we can call this method with that game object. Now we want to add new game objects to our game. Guess what we don't have to do? We don't have to modify the player class at all. We want to add more objects to our game? player class is unchanged. We don't have to write any new tests for the player class. We're only concerned with the object that we added. We're going to add a new object, we're writing a new class, we're extending game object, we're testing that new game object type, and we're confining our changes to that game object type. We're not messing with the player class at all, or anything that's going to interact with that. We shouldn't be updating our physics engine. We shouldn't be updating anything except that actual item that we're adding. And we should only be adding stuff pertaining to that item, pertaining to how that item interacts with the game world. We shouldn't be adding anything else, because everything else should be defined through inheritance in the game object class. So now that we have this parameter, we can create a new player and call useItem on either, I didn't update that one too, on either a dodgeball or a health potion. One method, and we have this implicit line, item of type game object equals dodgeball, which is of type dodgeball, or item of type game object equals potion, which is an object of type health potion. Both of these work because both dodgeball and health potion extend game object, so objects of those types can be stored in a variable of another type. And this is usually where that happens, is across a parameter being assigned to an argument. When we have a method, we'll have the method written for the base class, and then it can take any object that extends that base class. This is what starts giving us a lot more power. It gives our code a lot of flexibility. Now, thinking about our homework assignment, our project, this method call, and this method call implicitly, these method calls do very different things depending on the type of the object we give. So if we give it a dodgeball, the player is going to throw that dodgeball. If we give it a health potion, the player is going to heal. We didn't use any conditionals here. It just depended on the type of the item, the type of game object, which could be any one of the types of object in our game. Depends on the type to get different functionality. No conditional, no if this thing is a dodgeball, throw it. Else if it's a potion, heal yourself. We got none of that. We're just saying use the item. And then whatever implementation of the use method that's in the class, so dodgeball has a use method that it overrode, health potion has a use method that it overrode. So the method that's called here depends on the type of item, which is whatever type we called that method with. Polymorphism, it's awesome. If you don't believe me yet, I hope you will. You will someday. Might be after this class. Might be when you're off in 220, 250, maybe you'll understand. But polymorphism is sweet. It has the functionality here depends on the type, the object type, not the variable type. So remember, game object doesn't have an implementation of use. Game object doesn't even know anything about how to call the use method. All we did was say anything that extends game object has to have a use method that takes an object of type player. That's all game object does. The nice thing about that guarantee is that we can call that method through a game object variable. So we declare these abstract methods, which you might wonder, why did we even do that last time? We do that so when we have an object of type game object and we want to use polymorphism like this, we have a guarantee that that object has a use method that takes a player. We don't know what it does. We just know it's going to have it because game object, the abstract class, guaranteed it. It said, anything that extends me has to have a use method, so if you extend me, you better be overriding this use method and giving some functionality. So we don't know what it does. We don't know what this is going to do, this call to use, because it's going to depend on the actual type of the object stored in this variable, which in our case is either health potion or dodgeball, which did override the use method and provide an implementation. But which one of those methods is called depends on the type of the object stored in item. But we can access that method because it was defined in the GameObject class. That's why we use abstract methods. If we didn't have this here, and we just had the use method in each of the base classes, we wouldn't be able to call it here because we wouldn't be able to see that functionality from an object of type, from a variable of type GameObject. Right. Yeah, exactly. So the abstract class is defining the default behavior, which in this case is nothing. You don't even have to have any behavior at all. But you can have some default behavior here. If you have default behavior, then overriding is optional. But here, we are forcing everything to override. But we want to have this method signature here to say, hey, anything of type GameObject, you can call a use method, and we're going to guarantee that it will exist. By the time we have a concrete class, a class that's not abstract, it will have a definition for this use method. And it doesn't have to be an abstract class. If you define default behavior for both of these, you could delete abstract here. Just have it as a class. All right, everyone good up to this point? Let's see if there are any more questions in chat. Why not use the most defined types all the time? Because we wouldn't be able to do this. This would have to be two different methods. We would have to have one for dodgeball, one for health potion, one for bow and arrow, one for poison potions, I don't know, one for gold. We'd have to have one for every type of object that we can possibly have in our game, another one for swords. We don't want to do that. We want to code to GameObject, write this method once, and have it work for any possible GameObject that we can dream up in the future. This method will work for every single one of them, even the ones that don't exist yet. As long as they extend GameObject, which by design, we're going to make sure all our GameObjects extend GameObject, so it can have that is a relationship. You're damn right it's cool. I agree, Cole. Oh, come on. I want to add an emoji to it. My options are poop, bread, fork, and knife. Like, come on. All right, everyone good to this point? Yeah, I'll just react with poop. That means I love it. I agree. I'm changing the definition of the poop emoji. All right, let's see the next thing. So let's do some more polymorphism. Let's leverage this a bit more. The fact that we can store objects in types other than their type. We can store it in variables of any of its supertypes. On the surface, it seems like, why would we want to do that? So we saw one good example. Let's see another one. Let's say we want our players to be subject to our physics engine. We have our health potions and our dodgeballs extend GameObject. GameObject extends physics object, which would go off to our land of physics, and physics would be able to do all kinds of physics on that. Collision detection, gravity, taking the velocity in moving objects, all the good physics stuff that we want to have applied to our game. We're going to have all that code separate, and all that code in the physics engine is just going to work with type physics object. It's not going to know about players' dodgeballs. It's not going to know about our game at all. That's a good physics engine, something that's going to be completely generic, not know about the application at all, and just apply physics to whatever objects that it has. We're going to do that by using physics object throughout our entire physics engine, and then extending physics object in whatever we need, whatever we want physics applied to. So we did this to our other classes. We're going to do this to player too. Let's have player extend GameObject. Player is something that is in our game, that interacts in our world. It should have physics applied to it. We could have player extend physics object directly. It just depends on the functionality we want. I'm going to have it extend GameObject. And since GameObject extends physics object, now player is a GameObject and is a physics object. Now, if we want to have some physics in our game, we can do and assume that our physics engine, again, I scrapped the physics engine homework in the class, but what it would do, it wasn't called do physics, but it would update all of the physics objects in a game world, in any simulated world, it doesn't have to be a game, by taking a list of physics objects. So now we need a list of objects of different types. Now, this is something we take for granted in 1.15 when we're working with JavaScript and Python. If you want a list with different objects or an array with different object types in it, you just do it. You just do it in the language lets you, and that's fine. But in Scala, since we're strongly typed, every time we create a list, we need to give it a type parameter and say, your list of ints, your list of doubles, your list of strings. And those lists can only store that type. But now we want a list that can contain dodgeballs, health potions, and players, so we can give them all to our physics engine, and the physics engine can do its physics stuff. Well, we can't do that, but we can create a list, and physics is going to have no idea what to do with any of those types anyway. But what we can do is create a list of physics objects. So we create a list of physics objects, and now in this list, we can store any object of a type that extends physics object, either directly or indirectly. Here we have 3 types, health potion, dodgeball, and player, that all extend game object, and game object extends physics object. So all of these types, these 3 types, can all be stored in variables of type physics object. So since they can be stored in variables of type physics object and treated just like physics objects, store them in variables, call methods that take physics objects as parameters, and store them in data structures of type physics object. So we create a list of type physics object and throw all those 3 different types inside that list. We can mix and match these types. Any type that directly or indirectly extends or inherits physics object, we can stuff in this list. Now our physics engine, this doPhysics method, it takes a list of physics objects, and it doesn't care what those actual types are. All it knows is that those types extend physics object. Now inside our doPhysics method, we write all kinds of physics stuff, and we access anything defined in the physics object class, which is going to be, in this case, location and velocity. So we take the velocity, we update the location, we apply gravity if we're working in 3-dimensional space, and then we detect collisions. Are these 2 objects colliding with each other? We can do all that kind of stuff inside the physics engine. And we used to as a homework. You can probably find the old homework docs. You can still find that somewhere. I'm sure it's floating around somewhere out there. But we can do all that physics stuff on these objects of different types. Polymorphism. Polymorphism lets us do that. The list of type physics object, give it a whole bunch of things. As long as those things extend physics object, we can do this. Write your physics engine to work with physics objects. Anything that is needed for the physics engine, define that in the physics object class. And then everything else that extends physics object can add game-specific features. You can have methods that say, like, if I collide with another object, do whatever you want it to do. Write that code in those. But anything that, like, health points, our physics engine shouldn't be concerned with health points. Our physics engine shouldn't be concerned with throwing a ball, things like that. The physics engine will take care of everything after the ball is thrown and figure out the trajectory, build some nice parabolas and things like that. But it doesn't care about the features of our game. This is how we can have one game engine, or one physics engine, generally a game engine. But this is how we have one physics engine that can be used in multiple games. I'm sure you've seen this out there in the world. You play some games, some games have the same engine. They're built on the same engine. This is how we do it. Polymorphism. I don't know if they're exactly using polymorphism, but probably, most likely. All the mainstream ones are. But through polymorphism, we can make that happen. It helps us really reuse this code. That physics engine that they write, they don't know even which games are going to be built on top of it. The physics engine just works through some types defined for that physics engine, and then whenever somebody builds a game, you just say, extend these types, and then build all of your functionality on top of, on your classes. As long as those classes extend our types, physics can be applied to it. And it can be compatible with that physics engine. So that's polymorphism. Any other questions? Yeah, you can only use the physics objects. So only things defined in physics object, which for this example, I think I only had location and velocity defined in that class. But you can only access those things. So like in physics, we wouldn't be able to use like the use method, these game object methods, we wouldn't be able to use those inside the physics engine. But here's the beauty of it is we don't want to. Here's where we're going to define our game-specific things. Actually, object mass, yeah, you probably want that in the physics engine. Probably rearrange this a little bit for an actual game. Mass, you probably want to. But use, a player using an object, the physics engine doesn't have to care about that. So it doesn't need access to that. But over here, like say physics engine does all of its stuff, updates the location of all these objects. But over here in like potion 1, even though I stored it in a list of type physics objects when I gave it to the physics engine, so the physics engine couldn't access health potion specific functionality, but I still can, because I still have a reference in a variable of type health potion to that health potion. So these variables of the specific types, these are still stored in my game code. So in my game code, I can still use all of the functionality that I defined in these types. I just can't use it after those references are stored in physics objects and sent to the physics engine. But the physics engine does its thing, and then after that, I keep going doing my thing, my game code stuff, but the physics engine just, hey, here's a bunch of physics objects, do your thing. It updates all of the physics, and then I keep doing my thing in my game code. So just the polymorphisms that we make a type that stores many types, it's that we make a type that is many types. So health potion extends game object, extends physics object, extends any ref, extends any, which is all inheritance. And then after we use inheritance, once we have this inheritance tree, this inheritance structure, then we can use polymorphism, which polymorphism is when we have an object of one type, this object of type health potion, and we store it in a variable of a different type, in this case, a variable of type game object. So that variable of type game object stores an object of type health potion, which is 100% legal because health potion extends or is a or inherits game object. The first non-abstract child. So when an abstract class includes an abstract method, it's the first non-abstract child that has to implement that functionality. So you can have an abstract class with abstract methods. Abstract methods are the methods that we didn't define. We just said, like this is an abstract method because it doesn't have any equals and then braces. It doesn't have a body. It doesn't have a full definition. This is an abstract method. The first non-abstract class in the inheritance structure has to implement that. So we could extend game object with another abstract class and then not implement that yet. But as soon as we have a non-abstract, as soon as we say class something extends something, that extends game object, the first one that's not abstract has to implement all of the abstract methods. There can't be an abstract method left without a definition in a class that's not an abstract class. An abstract, for our purposes as programmers, abstract means you can't create an object of that type. You can't say new game object. If you say new game object, it's going to be a compiler error. You cannot create an object of type game object, but you can create objects of types that extend or inherit game object and store them in variables of type game object. So you can have variables of an abstract type. You can never have objects of an abstract type, at least not directly. You can create a dodgeball, which it is a game object through inheritance, but you can't say new game object. So if you ever want to say new whatever, that has to be a class, and it has to have all abstract methods in its inheritance tree fully implemented. Even if it's just like this returns unit, I could just say equals open brace, close brace. That's still a definition. It's not abstract anymore, but it has to be defined. Yeah, abstract is and if I tried to delete this abstract, I'd get an error because I can't have abstract methods in a class that's not an abstract class. So I have to have abstract here. If I fully implemented these, I could delete abstract here. Now let's talk about override. We saw this a little bit, but I want to talk about one more implication of override. So I said we extend any and any ref, and I'm telling you all this stuff about inheritance and polymorphism, but what about the any and any ref? Well, there's actually some functionality that we get from these. I believe both these methods are from the any class. Yeah, they have to be. From these classes, we actually get some methods. We get some functionality. We get some behavior. We get toString and equals are two very important methods to have in Scala. So toString, this is implicitly called whenever you do print line and give it some reference to an object. We can do that with anything in Scala because everything has a toString method because everything is of type any, and any has a toString method. So everything has a toString method. We do get some default behavior from this. There is behavior defined in the any class, or in any ref for this one. In any ref, that's going to print out like this. If you print out any object of a type that you've written, you're going to get this printed out. Object type at some reference, some at some whatever. So if we print out our health potions, we're going to get this kind of stuff that we see in the debugger. It's going to be a similar format to that, where you see type, at, and then some random stuff that we don't really care about. The one thing we care about with this is if they're the same. So if we do potion 3 equals potion 1, we didn't create a new potion here. This is an assignment by reference. So potion 3 and potion 1 store references to the same object on the heap, and we can see that right here, that they're the same reference, but potion 2 is some different reference. These are different objects. There's 2 potions in the heap, and we have 3 potion variables, so we're referring to 2 different potions. So we can see that useful, but not really. And then the default equals method, there's a dot equals, which is what is called through equal equal. If you're used to Java and you're wondering why I compare strings with equal equal, it's because in Scala equal equal calls dot equals. There is no equal equal operator. All the equal equal does is call dot equals. So dot equals by default is going to return true if those 2 objects, if those 2 references refer to the same object. So even though these 2 health potions have the exact same properties, they're effectively identical in every way, but since they don't refer to the same object, since potion 1 and potion 2 refer to different objects on the heap, we're going to get false here. No matter what we do, we're not going to get that to return true. Well, I shouldn't say no matter what we do, because we're going to change that in a slide or two. But potion 1 and potion 3, we can compare them by reference and say these variables refer to the same object on the heap. So equal equal by default with the objects you write, with the classes you write, objects of those types compared by reference. Do these refer to the same object? Again, kind of useful, but not really. I mean, that's usually not what we're concerned with. So we're going to override this functionality. So we can override that toString method in this way. So we have some class that we create. Here's the health potion that extends game object, which extends physics object, which extends any ref, which extends any. So all the way up in any, we got this default behavior from a method named toString with a signature that looks like this with no parentheses. And we can override that functionality and say, I don't want the default behavior anymore. I want whatever behavior I write. So we're going to override that toString. Has to look exactly like this. If you add the parentheses there, it's technically a different method, and you're going to get not the behavior you want. So you're going to override that, and then have it return any string you want. So whenever a health potion is printed to the screen, what format do you want? This is very useful in debugging if you're ever printing things to the screen. It's helpful to have meaningful strings and not just the reference, which is going to give us no meaningful information. If that's what you're printing in your hint strings in your tests, it's not very helpful. But if you override toString, you can get some better looking information on your side. And we can override, whatever we want here. We can also override equals. Equals is going to take a reference, not even a reference. It's going to take an object of type any, could be an any val or an any ref. So this could be like an int, just a straight up value, or reference to an object on the heap. And then we're going to use, this is the common practice, use a match statement and use cases to check the type of that object. And based on its type, do something different. So if this type, the way this code works, if this object is of type health potion, compare it by volume. Otherwise, return false. If this isn't a health potion, then it's not equal. And now we get significantly different behavior. It's same exact code, but now since we went into the health potion class and overrode the default toString and the default .equals, now we get way different behavior. We actually get the information of this, and since we're comparing this equal is now comparing by volume, which is 4 for both, we're going to get true for both of those. So we're comparing in something that's meaningful to our application, not comparing by reference and printing out references. Which brings us back to the lecture task with 1 minute. All right. See everybody Friday.